Welcome, I'm Professor Sever. Today we're going to discuss limits from the standpoint of review in Calculus 1. So slightly more in the next one, I call it an intermediate limit only because you have to factor the numerator and the denominator using the difference of cubes and the difference of squares. First, let's catch up and see why do we need to factor again. Can you evaluate, this is a rational function. Can you evaluate simply by plugging in? The answer is no, because you would get 0 in the denominator. 2 to the 4 is 16. 16 times 2 is 32. 32 minus 32 is 0. So you cannot plug in to achieve this limit. But we see that the numerator also goes to 0. 2 cubed is 8. 8 minus 8 is 0. This tells us that x minus 2 will be a factor of the numerator and the denominator. This is the factor theorem from college algebra. So we factor each expression separately. I factor the numerator by the difference of cubes, well-known formula. I first factor out a 2, and then I get x to the 4 minus 16. That's a difference of squares, which would be x squared minus 4 times x squared plus 4. Then I factor down the x squared minus 4 again using the difference of squares. Cancel. Pursuant to our theorem, functions that agree at all but one point is equal to the original limit, and this limit we can evaluate by plugging in, which is what I did. Let's look at the denominator. You have a 2 here. What's 2 plus 2? That's 4. What's 2 squared is 4. 4 plus 4 is 8. So we plug into the numerator. 4 plus 4 plus 4 is 12. And so we simplify, we get 3 over 16. Now the next one, I'm drawing the graph, but really at this point in the course, you would evaluate this limit. How? Well, first off, again, you have 0 in the denominator, 0 in the numerator. So that says it's an indeterminate form, which says to us that we must do more work to determine the answer. Now from the graph, it's pretty clear you have a jump discontinuity here, therefore the limit doesn't exist. But the work for us, the concrete version of the work would be the limit exists if and only if the limit from the left is equal to the limit from the right. So we will evaluate the limit from the left. The limit as x goes to 11 from the right of x minus 11 over x minus 11 is 1. The limit as x goes to 11 from the left of the absolute value of x minus 11 over x minus 11 is negative 1. And that's what I'm depicting here by the graph. The right-handed limit, which is 1, is not equal to the left-handed limit, which is minus 1. That's what we're depicting in the graph. Therefore, the limit does not exist. Just showing this graph is not really an analytical solution. I'm doing it for illustration. The preferred analytical solution here is to evaluate the limit from the left and the limit from the right. Okay, so let's look at this variation. So this one is an interesting technique. Now, we could use the change of variables technique on this one, but I'm going to illustrate a different technique, which is using a known trigonometric identity. Most of us recall from trigs and or pre-calculus that the sine of 2x is 2 sine x cosine x. So substituting in what that is, sine 2x is 2 sine x cosine x. The limit of the product is the product of the limits, so I can separate, and I'm also going to factor out the 2 all in one step. So I'm going to group this piece, sine x over x is one piece. I'm going to bring out the 5. The next step produces the following. It's 2/5 times the limit as x goes to 0 of sine x over x times the limit as x goes to 0 of cosine of x. Now again, this is the way we write it, but technically this separation is only valid if both of these limits exist, which we know they do. This is 1. And this limit is achieved by functional evaluation. It is also 1. So the final answer is 2/5. It's a nice example of using a well-known trig identity. Okay, let's look at some examples. And we'll provide an example for these 3 problems. And if there is one example, there's oftentimes many or infinitely many, so we'll just provide one, but we'll discuss it first. Give an appropriate example. All right, A. Give an example of a function f and a number c, real number c, such that the limit as x goes to c of f of x is 0. So this is just asking, can you think of a function whose limit is 0? Well, simple function is And by the way, I'm asking for two things, for the function f and the value of c. So I'm going to choose c to be 1, and f of x is x minus 1. And we know the limit as x goes to 1 of x minus 1 is 0. Example there are millions or infinitely many different examples. Any polynomial, for example, which is what I chose, what are the simplest limits to evaluate? Polynomial. So any polynomial where f of c is 0 would suffice, and this is just what I did. There would be other examples. Give an example of a function, g, such that the limit as x goes to 3 of g of x does not exist, but the limit as x goes to 0 of g of x does exist. Okay, so what this is really saying is I want to find the function g that has a limit that doesn't exist at 3, but at some other point, let's say 0, the limit does exist. A simple example would be g of x is 2 times the absolute value of 3 minus x over 3 minus x. Clearly, the limit at 3 doesn't exist because the limit from the left would not be the limit from the right. But what about 2? Well, the answer of 2, it would exist. Both the limit of the numerator and the limit of the denominator exist at 2, and the denominator is non-zero. Therefore, the limit here would be 2. 3 minus 2 is 1. 3 minus 2 is 1. The absolute value of 1 is 1. 2 over 1 is 2. And by the way, the limit of these, just in terms of that logic that I put forth, you have to be careful. Why does this d and e? Well, at 3, the limit of the numerator exists. At 3, the limit of the denominator exists. However, the denominator is going to 0, so we can't use functional evaluation, or we can't take the limit of the numerator over the limit of the denominator as the answer, because the limit of the denominator would be 0. Okay, so last example, give an example of a function h such that the limit as x goes to 2 of h is 5, but the limit as x goes to 2 of 3 of h is 10. Is that possible? The answer is certainly not. Let's look at that. Well, let's factor out the 3. Is 3 constant? Yes. So it could come outside of the limit. This would say 3 equal to 3 times the limit as x goes to 2 of h of x. Then you could divide both sides by 3, and that would give you the limit as x goes to 2 of h of x is 10 over 3, and that's not 5. So this would be impossible. That means there is no function h that satisfies those two properties. Therefore, it is impossible to give an example. All right, let's look at another problem. So now we have tangent 3 times tangent t over 11t. The first thing that you'll probably think about is moving those constants out of there. 3 and 11, they don't go anywhere. 3 doesn't go anywhere as t goes to 0, nor does 11. I mean, in a way, you could say, yes, 3 does go someplace. It goes to 3, but effectively, we know we can move those constants outside, so I pull the 3 over 11 as a fraction outside the limit, and now I would be just left with the limit 3 over 11 times the limit as t goes to 0 of tangent. And now I separate, tangent is sine over cosine, and then I separate the two limits. The limit of the product is the product of the limits, provided both pieces exist, which they do. This is our well-known limit of 1, and this is the secant function, which is defined at 0. So it's 3 over 11 times this limit, which is 1, times this limit, which is 1. And that gives you 3 over 11. Again, notice at this stage the limits are gone because it's at this stage that I evaluate both limits. So notice here in this problem, there are many ways to work it. The simplest way, I'm using the power rule type theorem. So notice the first thing in this problem you would note is the exponents are the same, 2 and 2, so I can use the squaring function and bring that 2 outside of everything. And now I let the limit pass to the inside, and then this gives me the limit as x goes to 0 sine x over x squared, and again that is our number 1. 1 squared is 1. Here's an example where we rationalize the denominator. Again, you can't plug in, which I should have gone back and mentioned that in this problem. You can't plug into this one using functional evaluation because the denominator would be 0 as x goes to 0. The same thing holds for part C. We can't plug in, namely we can't use functional evaluation because root 2 minus 2 is 0. So as t goes to 2, the bottom goes to 0. That's enough to say we can't plug in. We quickly observe the numerator also goes to 0. So we know it's an indeterminate form, 0 over 0, as a form, which means we have to do more work. First thing I will do is observe that 3 is a factor of both terms in the numerator, so I'll factor that out. Then I have t squared minus 4, which is the difference of squares. I'll factor that. Finally, I'll multiply by the conjugate of the denominator over itself, which is root t plus 2 over root t plus 2. And then I will, notice on the bottom, I have the difference of squares, and then I will just keep the numerator in factored form so I can achieve cancellation. Once we cancel, we now have an algebraic function that we can evaluate by functional evaluation. Again, there's no problem with this even radical because t is going to 2, not 0. So we just plug in 2 plus 2 is 4. The square root of 2 is the square root of 2. So we get 2 root 2 times 4 times 3, which is the answer. And again, I left it in factored form so you could see how the limit was achieved, but actually you would put 24 root 2 as your final answer. Now, for this problem, really you're using the limit of a composite function theorem, but you may think this is a dangerous value at 0 since this is an even radical. However, the limit will pass to the inside, and this is a polynomial which you would evaluate by plugging in. When you evaluate at 0, you get 12, so the final answer is the square root of 12. We know now this really works because the square root function is continuous at the number 12. Therefore, the limit can pass to the right, passes right through it to the inside, which is what I've done here. It's a nice way to write that. Kind of a high-level technique there. I'm Professor Sever. Thank you for watching a review of limits.